Uh, Good morning, everyone. My name is Grzegorz Sochacki, and I am coming from Bio-Inspired Robotics Lab at University of Cambridge, and I will talk about closed-loop action for robotic chef implementation. So currently, there is a numerous startups who are trying to do all sorts of chef bots, cooking robots, automated restaurants. And on the left, we have, for example, a Samsung chef, which is kind of built to work together with a human. So if it would have a problem, it would ask you for help, but it's not very capable. For example, it has problems with cutting ingredients and chopping. On the right, we have the mole kitchen, which is kind of, it seems to be very capable at cooking, but it's still just hard-coded, pre-programmed, and you need to give it like exactly the weight and exactly chopped ingredients. And on the lower part of screen, we have spice, which is using those kind of rotating woks to like stir fry you a meal, which is kind of classic automation approach, very simple yet working. And I think they have a few working restaurants in US. But all these robots have a huge problem. So the problem is they are kind of blind. They do not have all those feedback loops and intuitions human have. So for example, when you are cooking, you are able to taste what you are cooking, to smell it, you feel temperature, you actually smell when it's getting ready because it starts to start to emitting more smell. Then you have like tactile feedback to check out ingredients, etc., etc. So those robots miss them, and I think it's a chance to make some breakthrough if we add some of those feedback loops, so the robot actually know what they are doing, and then they can be more autonomous and hopefully cook for people without need for our work. So the first project I did was trying to implement some tactile sensor. So we took on workshop this movement of a human. When we are cooking something, we would stab it with fork to check how close to being cooked it is, which is forming pretty much a feedback loop for us, which is telling us how hard it is, and then putting together with our intuition, we know if we need to stop cooking or not. So here to replicate it, we build this very simple and cheap gripper. So we would run it with a motor with an encoder, which would pull this tendon. And the motor has an encoder, therefore we always know the length of a string, which allows us to do two things: to measure the size of object we grasp, because it will definitely change cooking time. And we also know when we are squeezing, we know by how much we are squeezing the object, which then combined with a force from another sensor allows us to measure a spring constant of the grasp object. And going to the force sensor, we went to like for a very simple implementation. It is just a silicon tube and pressure sensor. So we get the pressure from inside this tube. Therefore, when tube is pressed, of course, pressure is going up, and we pick it up. And we chose it because it's soft, so it prevents bruising, but also it's very quick to prototype, because imagine you are building it once and then you may rearrange the tube, check what works best. And then we of course need some kind of model. So imagine we can now measure this spring constant, but from there we also need to know how much it's cooked. So we just found a cooking model in literature, which assumed that there is just like uncooked area and fully cooked area, which is somewhat limited model, but it worked very well. And then we put together our full spring as those two springs in series. So then measuring the total spring constant, we can figure out how much of those two areas is there. So we know how deep it's cooked. And we have a little bit representation how it grasps the object. And I think the most important figure here is on the left top side, which was measured on potato, and it was quite a big one, so it took quite a moment to cook. But if you look at measurements, they're done at different times, so starting from raw to all the way to 60 minutes of cooking. And on x-axis, we know we have this this value, how much we squeezed by a distance and a force. Therefore, if you think about a slope here, it's a spring, it's a spring constant of the object squeezed, and we see that the slope is definitely going down when we are cooking more and more. Measurement is not perfect, but we usually take few of them and average, and then it works very well. And then if you look at the lower plot, that's how our average measurements are looking like against cooking time. So you would see that longer we cook, we definitely get the lower and lower spring constants, where there is of course some error there in some spaces, but overall the trend can be seen very good. So if we look at this model, it's after some maths, you may put it in a line equation, which we did on the left plot. So we have matched the model on one side, so which is a blue line, and then we just adjusted in the model for different sizes, and we just read the intersection with 0 there, and we have estimated cooking time for this given size of vegetable, and then we have tested it against a set cooking time. So if we just cooked it for a set amount of time, that's in green. So if you see some of them are below 0, especially the smaller one, which means they are quite overcooked, and then the bigger one, like over here, are quite raw, which means they are not cooked at all. But if we use our prediction, pretty much all of them are at level we want. Then another project we were doing was trying to do some closed loop for scrambled eggs. So if you look at this setup on the left, it's kind of early prototype, but it has this conductivity sensor on the top of the arm, which can actually distinguish white from yolk, and also can distinguish if there is salt there or no salt. So if we are taking quite a few samples with the sensor from the eggs, if we take a mean value, it will tell us how much salt is added. And then if you take a variance, it is giving you a good information about mixing. So what we usually do with this is setup for demonstration. We would ask you to cook your favorite eggs, and the robot would check them out with its sensor, try to cook its own eggs, and then measure the robotic cooking eggs, and then adjust in the control loop until it cooks the eggs same way as you do. So on the right, we see how the variance is falling down with amount of mixing. So it's exponential function. So it of course needs a little bit of readjustment. But we also see that the salinity mean is not changing too much where we are mixing. Therefore, the mean should be a good measure of amount of salt added. So if we want to see kind of how those measurement works, we have kind of 3x here without a salt added. So we see that the mean is quite stable, except if we like scramble them very strongly and don't do too much mixing as on the left. So the mean is a good measurement for amount of salt. And then there is a variance which definitely is falling down more and more mixing you are putting in. So that's a kind of a reference for you how it looks, how a certain looking egg would translate to the robot information. And we've run it on a few trials, which is we start with human cooked eggs, and then we have tries of the robot how it's going towards this those human cooked eggs, and we see that the errors are falling. Therefore, our control loop adjusted towards the eggs you have cooked. And if you have any questions, I am very happy to answer them. And thank you very much for your attention.